Black holes are among the most astonishing and mysterious features of our universe. At first glance, you might imagine them as dark, dense objects drifting silently through space. But that is not quite accurate. A black hole is not an object in the traditional sense. It is a region of space where gravity has become so intense, so overwhelming, that the very fabric of space and time is pulled inward, twisted into a singular point. There is no solid surface, no edge you could touch. Instead, it is pure distortion, a cosmic trap set by the universe itself. And what happens near this distortion defies common sense. Time slows, light bends, matter stretches into oblivion. The rules that govern your everyday life, motion, causality, even the idea of before and after, begin to break down. Yet none of this is fantasy. These are real phenomena, backed by unshakable mathematics and increasingly strong observational evidence. So join me as we cross the threshold into the unknown and try to understand what black holes truly are, not just in theory, but in the strange and astonishing reality of our universe. To understand how black holes are formed, we must begin with the life of a massive star. A star is not just a glowing ball of gas in the sky. It is a complex engine, a balance of two opposing forces. On one side is gravity, relentlessly pulling the star's mass inward toward its core. On the other side is the pressure generated by nuclear fusion deep within that core, pushing outward with heat and light. As long as these two forces remain in balance, the star lives on, stable and brilliant, shining across space for millions or even billions of years. Inside the core, hydrogen atoms are fused into helium under immense pressure and temperature. This reaction releases energy, which counteracts gravity and supports the star's structure. Over time, as hydrogen is depleted, the star begins fusing helium into heavier elements, carbon, oxygen, neon, and beyond. This process continues until the core starts producing iron. And here, the story takes a dramatic turn. Unlike lighter elements, fusing iron does not release energy, it absorbs it. So the delicate balance the star once held begins to fail. With no outward pressure to counteract gravity, the star's core collapses in on itself with unimaginable speed. The outer layers, no longer held up, fall inward and rebound violently off the now dense core. This sudden rebound creates one of the most powerful events in the universe, a supernova. In this explosion, the star ejects matter and energy across light years of space. The light from a single supernova can outshine entire galaxies. It is also where many of the universe's heavier elements, like gold and uranium, are forged in the extreme chaos. What remains behind after the explosion depends on how massive the original star was. If the leftover core is of intermediate mass, it collapses into a neutron star, an object about the size of a city, but with a density so extreme that a single teaspoon would weigh billions of tons. But if the star's core is massive enough, not even neutrons can hold up against the pull of gravity. The collapse continues, unrestricted, past every known physical limit. The result is a black hole, an entity so dense that space and time are crushed together into a singularity. This singularity, though invisible, is surrounded by a boundary known as the event horizon. Once matter crosses this boundary, it cannot escape, not even light. The formation of this horizon marks the moment a black hole is truly born. Unlike other objects, black holes do not possess a surface. They are regions of pure curvature, where the laws of physics as we know them begin to break down. Everything that falls in becomes part of the singularity's mass, and nothing ever comes out again, at least not in the traditional sense. So, in the death of a massive star, something entirely new is created. From balance and fusion to collapse and explosion, the final act of a star's life can lead to the birth of one of the universe's most mysterious and extreme phenomena. A black hole is not a corpse in the usual sense, but a transformation, a gateway into a realm where our understanding of reality is tested to its absolute limit. And all of it begins with gravity, the silent force that shapes stars, galaxies, and the very structure of the cosmos. As we approach the region around a black hole, the familiar rules of space and time begin to shift. Surrounding the singularity lies the event horizon, a boundary that marks the point of no return. It is not a physical surface you can touch, but a threshold in space beyond which escape is impossible. Even light, the fastest thing in the universe, cannot outrun the pull of gravity once it crosses this boundary. To an outside observer, anything falling toward a black hole appears to slow down, dim, and eventually freeze at the edge of the event horizon. This bizarre effect is not an illusion. It is a direct consequence of how mass distorts the fabric of space and time. According to Einstein's general theory of relativity, massive objects bend the spacetime around them. A black hole, with its incredible density, creates an extreme distortion, so intense that time itself slows to a crawl near its surface. From far away, we would never see an object actually cross the event horizon. It would appear to hang suspended in time, growing fainter as its light becomes increasingly redshifted into darkness. From the perspective of the falling object, however, the experience is very different. Time for the traveler continues as normal. There is no sudden transition, no jolt or barrier. They pass through the event horizon without even realizing it, but they are now cut off from the rest of the universe. No signal, no information, no message can reach the outside once they cross that invisible line. Within the event horizon, all paths forward in space lead inward, toward the singularity. There is no turning back and no standing still. What is truly staggering is how this distortion of space-time warps not just the trajectory of objects, but the very structure of causality. Space and time near the black hole become twisted so profoundly that their roles begin to blur. Time behaves like space, and space behaves like time. The normal order of events, cause leading to effect, can become scrambled, or even undefined. This is not simply science fiction. It is the logical extension of the mathematics of relativity, and it forces us to rethink what it means for something to happen. In this warped region of the universe, we encounter the ultimate boundary of knowledge. No experiment can be conducted from inside the event horizon that reaches the outside world. No observation can reveal what truly lies beyond. What we do know is that the laws of physics, as we currently understand them, reach their breaking point here. The singularity is hidden behind a veil, and the rules collapse at its feet. Black holes are not just cosmic curiosities. They are windows into the deepest structure of reality, a place where space folds, time stops, and understanding fades. For centuries, black holes were believed to be the ultimate prisons of the cosmos. Once something crossed the event horizon, it was gone forever. But in the 1970s, a groundbreaking idea challenged that belief. Stephen Hawking proposed that black holes might not be completely black after all. Through the strange lens of quantum mechanics, he discovered that black holes could emit radiation, slowly leaking energy over time. This was not science fiction. It was a theoretical necessity, born from the uneasy union of general relativity and quantum physics. To understand this phenomenon, we must dive into the concept of the quantum field. Contrary to intuition, what we call empty space is not truly empty. It is filled with invisible fields that vibrate quietly even in the absence of matter or light. These are known as quantum fields, and they exist everywhere in the universe. Each type of particle, electrons, photons, quarks, is a ripple in its own specific field. What we perceive as particles are actually resonances, momentary excitations of these universal fields. Even in a perfect vacuum, the quantum field never rests. Because of a principle called the Heisenberg uncertainty principle, we know that energy can briefly fluctuate, creating what are called virtual particle pairs. These pairs appear spontaneously, one matter particle and one antimatter particle, only to annihilate each other moments later. They pop in and out of existence like tiny blips, too fleeting to be directly observed. Yet they are real, and their effects can be measured. One experiment even detected changes in pressure due to these ghost-like fluctuations. Now, place a black hole in the middle of this churning quantum field. Near the event horizon, the rules change. If a virtual particle pair forms just at the edge, there is a small chance that one of the particles will fall into the black hole, while the other escapes before they can annihilate. To a distant observer, this escaping particle appears as radiation coming from the black hole itself. But energy cannot come from nowhere. The black hole must pay a price. The mass required to produce the radiation is subtracted from the black hole's total mass. This is what we now call Hawking radiation. Over cosmic timescales, it means that black holes are not eternal. They slowly evaporate, emitting tiny amounts of energy into space. At first, the process is incredibly slow, far too weak for our instruments to detect. But as the black hole shrinks, the radiation increases. Eventually, the black hole would radiate faster and faster, until in its final moments, it explodes in a burst of energy. A black hole dies not in silence, but in one last, spectacular flash of heat and light. Hawking's theory united the large and the small, general relativity and quantum mechanics, gravity and uncertainty. It hinted that even in the coldest, emptiest corners of space, something is always happening. The quantum field never sleeps, and in the presence of immense curvature, like that near a black hole, the hidden rhythms of the universe begin to sing. Hawking radiation is not just a trick of math. It is a reminder that nothing, not even the darkest corners of space, are truly beyond the reach of the laws of physics. For decades after Stephen Hawking first proposed his theory, the idea of black hole radiation remained purely theoretical. The mathematics was compelling, elegant even, but the universe offered no direct evidence. The problem was not in the theory itself, but in the scale. Hawking radiation, if it exists, would be incredibly faint, colder than the cosmic microwave background, and with wavelengths larger than the black hole's own event horizon. In short, it was undetectable with any instrument humanity had built. To observe it directly, we would need to wait until the universe itself grows cold and dark. But scientists are not known for waiting patiently. In recent years, researchers sought to recreate the conditions near a black hole, not in the vacuum of space, but in the laboratory. At the Technion Institute of Technology in Israel, a team of physicists led by Jeff Steinhauer created what is known as a sonic black hole. This is not a black hole in the gravitational sense, but an acoustic analog, a system in which sound waves are trapped in much the same way that light is trapped near an event horizon. It is a clever trick, exploiting the similarities between fluid dynamics and space-time geometry. The experiment used a cloud of ultra-cold atoms, chilled to near absolute zero, and arranged in a way that created a region from which sound waves could not escape. This acoustic event horizon mimicked the behavior of a real black hole, but at a scale small enough to manipulate and observe. And within this setup, something remarkable occurred. After nearly 100,000 repetitions of the experiment over more than 100 days, researchers detected faint emissions, vibrational energy escaping the system, just as Hawking had predicted. The radiation observed was not light, but sound, behaving according to the same equations that govern Hawking radiation. The results showed a thermal spectrum, meaning the energy followed the expected statistical distribution, exactly as a real black hole would emit. Though not a direct observation of a gravitational black hole, the experiment offered a powerful confirmation of the theory's foundations. It demonstrated that under the right conditions, horizons, whether of light or sound, can radiate, and they do so in ways that match Hawking's predictions. Of course, some skepticism remains. This was not an observation of a cosmic black hole, and analog systems have their limitations. But the success of the experiment does more than validate a theory. It shows that even the most abstract ideas, like radiation from the edge of nothingness, can be brought, in part, into the world of measurement and observation. It is a reminder that physics is not just about what we see in the sky. It is about what we can imagine, model, and eventually recreate, even if only as an echo of a deeper cosmic truth. For most of human history, we have assumed that matter is fundamental, that things, stones, stars, our own bodies, exist first, and space is simply the stage upon which they act. We see the world, we touch it, we weigh it, and we conclude that it is real in and of itself. Space, by contrast, feels like nothing, empty, passive, a blank canvas for reality. But what if we have had it backwards all along? What if space is not just a background, but a participant? What if the shape of space itself is what gives rise to everything we call matter? In Einstein's general theory of relativity, the presence of mass and energy tells space how to curve. That much is well known. The gravity we experience is not a force in the classical sense, but the result of objects moving along curves in space-time geometry. As physicist John Wheeler famously said, "Space tells matter how to move. Matter tells space how to curve." But here is the catch. The equations of general relativity do not tell us which comes first, curvature or mass. They are linked proportionally. Change one, and the other must follow. The direction of causality is not as clear as we thought. Imagine you are standing on a beach. You press your foot into the sand, and you see a footprint. The sequence seems obvious. Your foot caused the impression. But what if all you had was the footprint, with no memory of the foot? Could the imprint be all there was? Could it, somehow, give rise to the foot that made it? In the language of physics, we are beginning to ask whether the curvature of space-time, the warping of the geometric fabric of the universe, might be the cause of mass rather than its effect. This is not a philosophical trick. It is a serious question emerging from the mathematics of quantum gravity. In some models, mass is not a thing on its own, but a manifestation, a kind of shadow, of how space is shaped. Just as a hand cast against the wall creates a silhouette, matter may be a projection of deeper geometrical processes. We experience the shadow, but not the mechanism that casts it. What we call particles may simply be stable patterns in an underlying field of geometry, emerging only when space-time is curved in just the right way. In these models, the universe behaves not like a machine, but like a song. Fields resonate, space vibrates, and what we see as matter are just the harmonies, notes played by invisible instruments we have only begun to describe. It is a poetic notion, but not unscientific. In fact, it may be the only path forward in our attempt to unite the great pillars of physics, general relativity and quantum field theory. If these two frameworks are to be merged, we may need to rethink not only what the universe is made of, but what being made of even means. And if curvature gives rise to mass, the implications are staggering. It would mean that the black hole at the center of our galaxy is not a singular object, but a ripple in space so intense that it produces the illusion of an object. It would mean that your own body, every atom of it, is not truly solid, but a kind of standing wave, the result of the universe vibrating just so. Mass would not be an ingredient of reality, but a pattern within it. Something that emerges, not something that exists on its own. This line of thought inevitably leads to a haunting question. Are we real? If everything we are, our bodies, our memories, our thoughts, arise from curvature, are we merely the echoes of something deeper? Perhaps. But even if so, it changes nothing about what we feel. We laugh, we cry, we dream, we love. Whether we are the hand or the shadow, the singer or the song, the experience is real to us. And maybe that is what matters most. But for the curious mind, the idea that matter might be born from space itself is not the end of wonder. It is only the beginning. Black holes do not merely bend space and time, they twist it. When a massive object spins, it does more than rotate in place. It drags the fabric of space-time around with it, creating a spiraling distortion that stretches far beyond its event horizon. This effect, predicted by general relativity and later confirmed through precise measurements near Earth, is known as frame dragging. But in the case of a rotating black hole, it becomes more than a subtle nudge. It becomes a whirlpool, a violent, unavoidable spiral in which space itself is being dragged along at nearly unimaginable speeds. Just outside the event horizon of a rotating black hole lies a region called the ergosphere. In this zone, space is spinning so quickly that no object, no matter how powerful, can remain stationary with respect to the outside universe. Everything is pulled along in the direction of the black hole's spin. Even light is affected. If you were to shine a flashlight in the opposite direction of the spin, the beam would still be swept forward. It is not that the light is slow. It is that space-time itself is moving beneath it, like a conveyor belt set faster than any runner can resist. This effect may sound like a strange curiosity, but it has astonishing implications. In the 1960s, physicist Roger Penrose suggested that the ergosphere could be used to extract energy from a black hole. By sending a spacecraft or object into this region and splitting it in two, one part could fall into the black hole while the other escapes. If done correctly, the escaping piece could gain more energy than the original object had. This process, now known as the Penrose process, shows that black holes might not only consume energy, they might give it back. How is this possible? The answer lies in the structure of the ergosphere. Because of frame dragging, energy and momentum are not fixed in the usual sense. In certain paths within the ergosphere, an object can have what is called negative energy relative to an outside observer. When this negative energy object is absorbed by the black hole's total mass and spin decrease. The remaining object, now freed from the ergosphere, escapes with more energy than it started with. The laws of physics are not broken. They are simply bent in extraordinary ways. This strange redistribution of energy leads us to an even more provocative idea: the possibility of faster-than-light travel. General relativity tells us that nothing can move through space faster than light, but that rule applies only locally. It is possible for space-time itself to move, to stretch, or to bend at any speed it likes. This is how the expansion of the universe allows distant galaxies to recede from us faster than light without violating any laws. And near a spinning black hole, frame dragging creates a region where the very fabric of space is moving faster than light. From the perspective of someone far away, it appears that anything caught in the ergosphere is moving impossibly fast. But to an observer within that spinning frame of reference, everything still follows the usual rules. Light is still the limit, locally. However, if we could somehow harness the motion of the ergosphere or recreate its conditions, we might move through space without actually moving in the traditional sense. Like a surfer riding a wave, we could let the structure of space itself carry us, allowing for apparent speeds faster than light without breaking the cosmic speed limit. It may sound counterintuitive, but falling into a black hole is not as easy as it seems. Despite being the most powerful gravitational wells in the universe, black holes are surprisingly hard to enter. Most matter does not dive straight in. It orbits, it resists, it spins. That is because of a fundamental law of physics called the conservation of angular momentum. Any object approaching a black hole will almost always have some sideways motion. As it draws closer, that motion increases, causing it to spiral around the black hole instead of plunging directly inward. This spiraling matter forms what is known as an accretion disk, a thin, flat ring of gas, dust, and stellar debris rotating around the black hole at incredible speeds. Within the disk, particles rub against one another, creating friction so intense that the temperature soars to millions of degrees. These disks shine with brilliant energy, emitting powerful X-rays and even visible light. In fact, some of the brightest objects in the universe, called quasars, are powered by the violent brilliance of supermassive black holes feeding on their accretion disks. What is remarkable is that these disks are not static. They are dynamic engines of transformation. As matter moves inward through the disk, it sheds energy and angular momentum. This allows it to sink deeper into the black hole's gravity well. In the process, up to 40% of the infalling matter's mass can be converted into energy. For comparison, the nuclear fusion that powers our sun converts less than 1% of mass into energy. This makes accretion disks among the most efficient energy sources known to physics. But that is not the only story unfolding here. In some cases, black holes do not just consume matter, they launch it. Emerging from the north and south poles of certain black holes are narrow, focused beams of material traveling at nearly the speed of light. These are called relativistic jets. They can stretch across entire galaxies and beyond, sometimes reaching lengths of millions of light years. And yet, the black hole itself is not expelling this matter. It is being channeled and ejected by the extreme environment just outside the event horizon. The exact mechanism behind these jets remains a subject of intense study, but most theories point to magnetic fields. As the accretion disk spins, charged particles generate intense electromagnetic forces. These forces twist into colossal magnetic spirals, funneling energy and matter away from the disk and out through narrow escape routes along the poles. Like steam bursting from the spout of a kettle, this matter escapes in focused streams, carrying away angular momentum and helping regulate the growth of the black hole. Relativistic jets are so luminous and far-reaching that we can observe them across billions of light years. In some galaxies, we see one bright jet aimed toward us, while its twin jet remains invisible, pointing away, its light lost to the cosmos. This asymmetry is not due to imbalance, but to relativity itself. The jet coming toward us appears brighter due to a phenomenon called relativistic beaming, where motion near light speed compresses radiation into a single direction. These jets are not just cosmic fireworks. They are signals, messages from the edge of the known universe. When we think of black holes, we often imagine stellar remnants, objects born from the deaths of massive stars. But scattered throughout the universe are monsters of an entirely different scale. At the centers of galaxies, lurking behind veils of gas and light, lie supermassive black holes, cosmic giants with masses millions to billions of times greater than that of our Sun. Unlike their smaller cousins, these black holes did not come from a single star. Their origins remain a mystery, but their presence shapes the structure and evolution of entire galaxies. Among these giants, one stands above the rest. Its name is TON 618, a quasar so powerful and distant that its light has traveled across more than 10 billion years to reach us. At its core is a supermassive black hole weighing an estimated 66 billion solar masses. To put that in perspective, this single object outweighs our entire Milky Way galaxy. Its event horizon is so vast, it could contain multiple solar systems with room to spare. Yet what we see is not the black hole itself, but the brilliant accretion disk that surrounds it, shining brighter than thousands of galaxies combined. It may seem strange that the most massive black holes we know of are also the most distant. Should not older black holes closer to us have had more time to grow? The answer lies in how we detect them. Many of the largest black holes are identified by their quasar activity, the brilliant outbursts that occur when enormous quantities of gas fall into the black hole's disk. These events are more common in the early universe, when galaxies were younger, richer in gas, and more chaotic. Today, most galaxies have calmed, and their central black holes lie in silence. There is also an observational effect known as Malmquist bias. Simply put, we are more likely to detect the brightest objects in the sky, especially at great distances. Quasars are among the most luminous phenomena in the universe, so they stand out against the cosmic backdrop. In contrast, a supermassive black hole with no active accretion disk is virtually invisible. It emits no light, no X-rays, no signature we can easily detect. This means there may be equally massive black holes much closer to us, but without the brilliant glow of a quasar, they remain hidden in the dark. Over time, the universe has changed. The early cosmos was dense and energetic. Galaxies collided more frequently, funneling gas into their centers and igniting quasar activity. But as the universe expanded and cooled, gas became scarcer. Much of it formed stars or was ejected into intergalactic space. Many galaxies today are considered red and dead, elliptical giants that no longer form new stars. Their black holes, having consumed the available gas, now sleep in silence. The age of the quasar is fading, and with it, our ability to spot the most extreme black holes. This cosmic quietude may mislead us into thinking the universe is growing tamer. But the black holes are still there, older, heavier, more patient. Some lie at the hearts of spiral galaxies like our own, quietly influencing the stars around them. Others hide in elliptical galaxies, shrouded in silence. Our ability to detect them depends on rare alignments, lucky timing, and ever-advancing technology. The Event Horizon Telescope gave us our first image of a black hole's shadow, and future instruments may finally reveal the sleeping giants hidden throughout the cosmos. So while the brightest, farthest quasars may steal the spotlight, the story is far from over. The largest black holes are not just relics of the early universe. They are still growing, still shaping the galaxies they inhabit. They may hold answers to some of our deepest questions about gravity, time, and the fate of all matter. But to find those answers, we must learn to see in darkness, to read the quiet signatures left behind by objects that bend space and time itself. The giants are not gone. They are waiting. Black holes challenge our understanding of physics, but they also open doors to possibilities even stranger than themselves. When we explore the full mathematical structure of a black hole, not just as it exists in our universe, but as it is described by general relativity, we encounter something remarkable. The equations do not merely predict a one-way gravitational trap. They suggest a mirror image, a region of space-time that nothing can enter, but from which things might emerge. This hypothetical region is called a white hole, and it is the theoretical opposite of a black hole. To visualize how all of this fits together, physicists use something called a Penrose diagram. It is a compact way to represent an entire infinite spacetime within a finite image. In these diagrams, time flows upward, and light always moves at 45-degree angles. A standard Penrose diagram of a black hole includes 4 distinct regions: our observable universe, the black hole itself, a parallel universe, and, at least mathematically, a white hole in the past. Matter can fall into the black hole, but nothing can return. Meanwhile, The white hole expels matter, but cannot be entered. This extended diagram is not merely a drawing trick. It emerges naturally when solving Einstein's equations for a static, eternal black hole. Of course, real black holes are not eternal. They are born from collapsing stars, which means parts of the extended diagram do not apply to the physical world as we know it. Still, the mathematics remains internally consistent. And that raises a profound question. If the math allows for white holes, might the universe allow them too? Or are they purely mathematical artifacts, destined to remain forever unobserved? Things become even more interesting when we add rotation. Most real black holes spin, and when this rotation is included in the equations, the Penrose diagram becomes far more complex. The singularity at the center of a rotating black hole is not a point, but a ring. The presence of spin creates new regions of spacetime within the black hole, zones where time and space exchange roles, and where causality becomes deeply uncertain. In some of these regions, the geometry bends back on itself, allowing for the possibility of closed time-like curves, loops in time. These new regions also include what we might call a wormhole, a tunnel through spacetime that connects one universe to another. In theory, it is possible to enter a rotating black hole and emerge elsewhere, not just in a different location, but in a different universe entirely. This is not science fiction. It is a direct consequence of extending the mathematics of general relativity. The wormhole forms a bridge between two disconnected spacetimes, connected through the black hole's interior. And at the other end, there may be a white hole, spitting out what fell in. Unfortunately, this beautiful idea comes with serious problems. The structure of a wormhole is unstable. Even the smallest disturbance, such as a single photon passing through, can cause the tunnel to collapse. Moreover, the laws of quantum mechanics suggest that the singularity may not exist as described by classical relativity. Instead, it may be replaced by something else entirely, something we cannot yet describe. In other words, while the Penrose diagram suggests a path through a black hole, our current understanding of physics tells us that the bridge may close before anyone can cross. Yet, some physicists believe white holes might still exist. One theory proposes that when a black hole finishes evaporating via Hawking radiation, the end state is not empty space, but a white hole. In this view, the white hole is not a twin of the black hole, but its final chapter. The information and matter that once fell into the black hole could be released back into the universe in a delayed but complete form. If true, white holes may offer a solution to the information paradox, a problem that has haunted physics for decades. So far, we have not observed a white hole, nor confirmed the existence of a traversable wormhole. But the mathematics that describe them are not imaginary. They are part of the same framework that gave us gravitational waves, time dilation, and the bending of starlight. Phenomena once thought impossible, now measured with precision. Whether white holes and wormholes exist in our universe remains to be seen, but their place in the equations reminds us that reality may be far deeper and far stranger than our senses would ever suggest. We spend our lives surrounded by solid things, objects we can touch, lift, and measure. Chairs, stones, bodies. We think of them as real in a simple, self-evident way. But modern physics paints a very different picture. The deeper we look, the less solid everything becomes. Atoms are mostly empty space. Particles are not hard little spheres, but excitations in invisible fields. And mass itself, the quality that gives something weight, may not be intrinsic at all. It may arise entirely from the curvature of space and the interplay of energy with geometry. This is not metaphor. In general relativity, there is no such thing as a force of gravity in the traditional sense. What we experience as weight is really just our resistance to the bending of spacetime. We are not pulled down, we are pushed along curved paths. And in quantum field theory, particles are not objects floating in space. They are the space. Every particle is a ripple in a quantum field, and every field permeates all of space. When you look in the mirror, you are not seeing a thing. You are seeing a pattern. So what, then, are we? If the atoms in your hand are mostly void, and their properties are defined by fluctuations in invisible fields, and those fields themselves are shaped by the bending of space, then what remains of you? Perhaps you are not a thing at all. Perhaps you are the shape of space in a particular region, a configuration of energy, a temporary arrangement of quantum waves held together by rules we are only beginning to grasp. If so, then your existence is not about stuff. It is about form, vibration, structure. There is a thought in theoretical physics that lingers like a whisper, that matter may be an illusion born of geometry, that everything we see and feel is simply the way curved space expresses itself. If this is true, then your body, your thoughts, your memories, they are all shadows. Not in a negative sense, but in the same way that light is a shadow cast by energy, or sound is a shadow cast by pressure waves in air. You are the echo of something deeper, the reflection of structure in motion. This idea is not mystical. It arises from the most rigorous mathematics we possess. The equations of general relativity, quantum field theory, and even string theory all point toward a reality in which substance is secondary. Geometry comes first. From geometry, energy arises. From energy, matter takes form. And from matter, minds like yours begin to ask questions. In this view, consciousness is not a ghost in the machine. It is a pattern in the song of spacetime, brief, brilliant, and possibly inevitable. If you are a ripple in the fabric of reality, does that make you less real, or more? The ocean wave is not separate from the sea. The flame is not separate from the fire. You are not floating above reality. You are of it, through and through. And though your form may dissolve, The fields remain. The geometry continues. The song plays on, in new verses and new voices. Perhaps the deepest truth is this: that to be real is not to be permanent. It is to participate in the unfolding of something far greater than yourself. So the next time you look at your hands, your breath, the stars above, remember what they are: not objects, not things, but processes, patterns, moments in a long and beautiful equation written across the universe. You are not standing on solid ground. You are riding a wave of curvature and light. And the question of what is real may never be answered fully. But perhaps that is all right. Because to ask the question, to wonder about it at all, is already to be a part of the answer. Throughout history, technology has been the great translator between imagination and reality. What begins as myth or dream, flight, communication across oceans, walking on the moon, eventually becomes a blueprint, then a machine, then a memory. Today, we stand on the edge of another myth, one that has haunted physics for more than a century: the dream of bending time and space. Not merely to travel faster or farther, but to rewrite the rules that seem to bind us, to move through time, cross immense distances instantly, or perhaps even return from beyond the stars. At the center of this dream lies a strange truth. Black holes may not only consume energy, they may also give it back. The idea is rooted in the rotational energy of spinning black holes, particularly in the region known as the ergosphere. Here, frame dragging twists spacetime so violently that energy can, in theory, be extracted. This concept was first proposed by Roger Penrose in the form of the Penrose process. While still far from practical, it suggests that the future may hold technologies that tap directly into the dynamics of curved spacetime itself, opening a path to vast new energy sources. Imagine a civilization advanced enough to harness that rotational energy. With precision machines orbiting safely within the ergosphere, converting motion into usable power, entire star systems could be sustained. Propulsion, computation, even artificial wormholes might become feasible. This is not just speculation, it is an open question in physics. We do not yet know what is possible at the intersection of extreme gravity and high technology. But if the rules of general relativity continue to hold, then black holes are not only cosmic prisons, they are also potential engines. And then there is the wormhole, a theoretical tunnel through space-time that could, in principle, connect two distant points across the cosmos, or even two moments in time. Wormholes arise naturally in the mathematics of Einstein's equations, especially in the extended geometries of rotating black holes. But most such wormholes are unstable, collapsing too quickly for anything to pass through. Some physicists speculate that with the right form of exotic matter, something with negative energy density, a wormhole could be held open, long enough for a traveler or signal to pass through. If such a structure could exist, it would revolutionize our understanding of distance, time, and causality. A wormhole could link a planet orbiting Alpha Centauri with Earth, allowing instant travel across 4 light years. Or it might connect the distant future with the ancient past. Paradoxes abound, of course. Grandfather problems, closed time-like curves. But many of those paradoxes may be resolved by the probabilistic nature of quantum mechanics, or by deeper laws we have yet to uncover. Time travel remains speculative, but it is not nonsense. It is permitted, at least on paper. More cautious theories focus not on breaking the speed of light, but on sidestepping it. The Alcubierre drive, proposed in the 1990s, imagines a bubble of spacetime that contracts in front of a ship and expands behind it, moving the vessel without violating the laws of relativity. The ship never exceeds light speed locally, but the space around it does. Though the concept requires negative energy, and perhaps technologies far beyond our reach, it shows that faster-than-light travel is not forbidden by the laws of physics, only by the limits of what we can build. Such ideas often sound fantastical, but so did rockets, satellites, and computers once. The path from dream to reality is rarely smooth. It is built on centuries of patient work by engineers, theorists, experimenters, and yet progress is real. We have photographed the shadow of a black hole. We have measured gravitational waves from colliding singularities. We are already testing solar sails, antimatter engines, and quantum communication. The seeds of tomorrow's interstellar voyages may already be blooming in the labs and classrooms of today. But perhaps the greatest transformation will not be in our machines, but in our minds. To travel beyond the stars, we must first imagine what lies beyond our current limitations. We must reimagine space not as distance, but as structure. We must stop thinking of time as a line and begin to see it as a landscape, curved, folded, entangled. If wormholes and warp drives are ever to exist, they will not come from brute force, but from insight, from a deeper understanding of the very fabric of reality. The future of space-time travel is not written yet. It may take centuries, or it may never arrive at all. But the questions we ask now will shape what is possible. Whether we learn to ride waves of curvature or open tunnels through dimensions, the journey has already begun, in equations, in thought, in story. And if humanity ever leaves the cradle of its own sun, it will not be by breaking the universe's rules, but by learning to dance with them. We began with a question: what is a black hole? Along the way, we found something far more profound. We encountered places where time slows and space warps, where light cannot escape and matter dissolves into pure geometry. But the story does not end there. Some physicists now wonder whether the Big Bang itself, the moment our universe was born, might resemble a white hole, erupting from the other side of a collapsed geometry. Perhaps the universe is not a closed chapter, but a cycle, or a bridge between regions of a reality larger than we can currently imagine. In the years ahead, we may witness something even greater, the unification of quantum theory and spacetime geometry. A single framework that explains not only black holes, but the origin of the cosmos, the flow of time, and perhaps even consciousness itself. But for now, we are explorers, standing on the shore of a vast, dark sea, listening for echoes in the silence. You have just journeyed through singularities, horizons, and hidden symmetries. If that sparked your wonder, subscribe, because this is only the beginning. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.